Hello everyone, welcome to chemistry class. This is the first topic in our chemistry syllabus, some basic concepts of chemistry. In this chapter, we'll be going through the concepts of chemistry, the tools that are required for further learning of this topic. Now, I'll be providing a readout, so I suggest you go through the definitions, and then I also urge you to learn at least the first 30 elements in the periodic table, starting from hydrogen to zinc, along with their atomic number and molecular mass. I hope you'll feel at ease if you know those. Now, to begin with, let's try and define what is chemistry. Chemistry is a topic. Chemistry is the study of interaction of matter and their outcome. Matter, as we all know, is anything that occupies space and has mass. Now, if we recall Dalton's atomic theory, he suggested that matter is made up of very small indivisible particles called atoms. Now, we can classify matter into two broad categories on the basis of their physical nature and on the basis of their chemical nature. So now, as you can see, matter can be classified in this way. So according to the physical state, we can classify matter into three broad categories: solid, liquid, and gas. And on their chemical state, we can classify matter into pure and mixtures. Now, under mixtures, it can be homogeneous or heterogeneous, depending on the uniformity of the mixture. And the pure substances are made up of elements and compounds, pure compounds. Now, one of the most important concept that emerged from Dalton's atomic theory was that he tried to define the mass of an atom, which he called the relative atomic mass. Now, this is a ratio that, or a standard reference to which he tried to attribute or tried to classify the masses of different atoms. Suppose he took the reference as hydrogen atom. That means all the masses he divided with the mass of a hydrogen atom. Like suppose mass of any element, mass of an element, he divided it with the mass of one hydrogen atom. Relative atomic mass. Now, further on, scientists defined the relative atomic mass in terms of oxygen, which we call the oxygen scale. Relative atomic mass in terms of oxygen. So we divide mass of an element with 1/16 into mass of an oxygen. That will give us the relative atomic mass of that particular element. Now, of one oxygen atom. But these days we define the relative atomic mass of any element by carbon 12, or the mass of carbon 12, which we just replace this by 1/12, because that is the mass of one atom of C12 atom, carbon 12 atom. Now, from this relative atomic mass, we can define an atomic mass unit. Atomic mass unit. One atomic mass unit is equal to 1 by 12th mass of C12 atom. Now, which is approximately equal to mass of a nucleon, mass of one nucleon of C12, carbon 12 atom, which is approximately equal to 1.67 into 10 raised to the power minus 24 grams, or yes, grams, or 27 kilograms. Now, one atomic mass unit is also called as Dalton. Now, these days we simply refer to atomic mass unit as U, or unified mass. So 1 AMU is equal to 1 unit. That's how we define these days. From the atomic mass unit, we can define what is a mole. A mole is an important concept in chemistry. This mole is the standard frame of reference for all the elements in, or the compounds or molecules. Now, what is a mole? It's just a number. It is equal to 6.023 into 10 raised to the power 23 particles, or entities, particles. Now, in 1 by 12th mass of an atom, mass of C12 atom, or 0.012 kg of C12 atom, we have this much number of particles. Oh, sorry, not atom here. This 0.012 kg of carbon C12, we have this much atoms. So mole basically is the standard reference for different molecules or atoms or elements. Suppose 1 mole of hydrogen will have this much number of particles or atoms. 1 mole of oxygen will also have this much number of atoms in it, and this number 6.023 into 10 raised to the power 23 particles is also called as the Avogadro's number, and it is denoted by Na. So this mole concept gives rise to our gram atomic mass. Now, what is a gram atomic mass? It is defined as the atomic mass of an element expressed in grams, or simply the atomic mass of an element expressed in grams is called gram atomic mass of that element. For example, let's take the atomic mass of oxygen for oxygen, atomic mass of oxygen, mass of oxygen atom is equal to mass of one oxygen atom, which is equal to 16 atomic mass unit. Now gram atomic mass is equal to mass of 6.02 into 10 raised to the power 23 oxygen atoms, which is equal to 16 atomic mass unit into 6.02 into 10 raised to the power 23 grams into 6 point into 1.67 into 10 raised to the power minus 24 grams. Now this is equal to 16 grams. Since this and this are equivalent to 1, you can calculate and see. So which suggests that oxygen atom or gram atomic mass of oxygen is 16. Now we can also calculate the molecular gram molecular mass in the same way. Now in molecule, suppose oxygen molecule, it has 2 parts of oxygen, so we just multiply this answer because we know the gram atomic mass of oxygen, which is 16, and we have 2 for molecule, 2 atoms of oxygen, so the gram molecular mass of oxygen would be 16 into 2, which is 32 grams. Here is a simple relation of the mole with the number of species, volume, and mass. If you want to find if you want to convert from mole to volume, you just have to multiply it with 22.4 liters, then you'll get the volume. Or if you divide volume by 22.4 liters, then you get back mole. Same way, if you multiply mole with number of the Avogadro's number, then you get the number of species or atoms. And that number of atoms or species, if you divide with Avogadro's number, you get back the number of moles. Similar to find out the mass, you just have to multiply with molecular weight or atomic weight the mole, then you get mass, total mass of that particular compound or atom. And if you divide the molecular weight or atomic mass of the mass that is given to you, then you get back the number of moles. So this is a small relationship between mole, number of species, volume, and mass. So our next discussion is percentage composition, and here we are going to find out the percentage of each element in the compound by knowing the molecular formula of a compound. We know that according to the law of definite proportions, any sample of a pure compound always possesses constant ratio with their combining elements. To understand the percentage composition, let's work out an example. Now this is the question that we want to solve in trying to understand the percentage composition. I suggest you pause the video and try to solve this question. Okay, so let's try to solve the problem. Now, for mass percentage, the solution, mass percentage of nitrogen in ammonia. So in the question, it's equal to it's given that the mass of nitrogen in 1 mole of ammonia, and mass of 1 mole of ammonia. Mass of 1 mole of ammonia into 100. So mass of nitrogen in 1 mole of ammonia is given as 14 grams, and then mass of 1 mole of ammonia is 17 grams. This gives us around 82.83 percentage. Oh, sorry, 35, and mass percentage of hydrogen in ammonia, same way. Mass of hydrogen in 1 mole of ammonia over mass of ammonia, 1 mole of ammonia, 1 mole into 100. So given the mass of hydrogen in 1 mole of ammonia is 3, and the mass of 1 mole of hydrogen is 17 grams, so which gives us 17.65%. That's how we calculate the percentage composition in each compound. Now, after knowing the percentage composition, let's try to make out what is an empirical and molecular formula. We have just seen that knowing the molecular formula of a compound, we can calculate the percentage composition of the various elements associated with it. So if we know the percentage composition of the elements initially, we can calculate the relative number of atoms of each element in the molecules of the compound. This gives us the empirical formula of the compound. Further, if the molecular mass is known, then the molecular formula can easily be determined as well. Now, what is an empirical formula? The empirical formula of a compound is a chemical formula showing the relative number of atoms in the simplest ratio. So empirical formulas simply means it's a ratio, or of the simplest form. An empirical formula represents the simplest whole number ratio of various atoms present in a compound. The molecular form, on the other hand, the molecular formula gives the actual number of atoms of each element in a molecule. The molecular formula shows the exact number of different types of atoms present in a molecule or in a molecule of a compound. The molecular formula is an integral multiple of the empirical formula. So, as we have heard just now, that the empirical formula is the simplest whole number ratio of a particular compound. Therefore, if we know the empirical formula, we can easily calculate the molecular formula, and vice versa. To understand this, let's try and solve another example. So here's the question. Now, they have given us the empirical formula. Acetylene and benzene, we know both are hydrocarbons, so their empirical formula is CH. The molecular masses of both acetylene and benzene are given, 26 and 78 respectively. So we are asked to deduce their molecular formulae. Now, since the empirical formula is given, so the first step is is to know the the first step is to know the mass of the empirical formula. Suppose the empirical formula, the empirical formula of compound is given as a CNH. So therefore empirical mass, empirical molecular mass, or empirical formula mass. So we know that carbon is 12 and hydrogen is 1, so which gives us 13. And therefore the molecular mass would be this into 2, which is equal to 26. Now there is a relation between this molecular mass and the empirical formula. So molecular mass is equal to n times the empirical formula mass. Since, as we know, that the empirical formula is the simple whole number ratio, or the simplest ratio of this molecular mass, therefore we multiply it with this entity n, which we don't know. So in order to know this unknown entity, we just have to molecular mass over empirical formula mass. Then we'll find this unknown entity, and we'll use that. We'll apply this equation, the above equation. Now let's plug in these numbers in this equation. So the unknown quantity n is equal to, this is the given molecular mass of acetylene over the calculated empirical formula mass, which is 2. So for acetylene, we know that empirical formula is CH, so we just have to multiply it with n to get our molecular formula, which n is which is equal to our molecular formula. So since this n is 2, CH into 2, so we get C2H2. So this is the molecular formula of acetylene. In the same way we can calculate for benzene. Now benzene, given molecular mass is in the question is 78. So 78, and the calculated empirical formula mass is 13. So we get 6, which is our n, the unknown entity. So if we multiply this again, same way, CH into 6, then we get C6H6 for benzene. Now I'll give you another question which you can try. You try to solve this question. If you have any queries regarding this, you can personally WhatsApp me in my number. So that is the molecular formula which you should arrive if you calculate it properly. Okay. Now these are some important concepts in chemistry. molarity, normality, and mole fraction. The molarity is basically the moles of solute per volume of solvent into 1000 ml, and molality is moles of solute over mass of solvent into 1000 grams. Normality, gram equivalent of solute over volume of solvent into 1000. Mole fraction means moles of solute, either A or B. If a compound if a compound has two parts, A and B, so to find the mole fraction of either A or B, we divide moles of solute A over moles of solute A plus moles of solute B. Or if you want to find B, similarly, moles of solute B over moles of solute A plus moles of solute B. That's how we find the mole fraction. If it's more, suppose if there are three A, B, C, there are three different parts, then we'll do similarly for, and then we have moles of solute A plus B plus C, and then for all individual entities we calculate mole fraction in that respect. Again, these are also some important relations for percentage calculation of concentration. If you want to calculate weight by weight, weight by volume, or volume by volume, then you need to know these relations. You can calculate easily. Okay, I think this is enough for the first chapter. If you have any queries, you can leave a comment or you can contact my number. Thank you.